Good evening. This is the project I was given to, and my project is basically the investigation of oscillatory flow across complex geometries. And Mr. Ibrahim is the original author, and I have done few extra simulations for this phase. I will basically give you a recap of what I did so far and move from there. So to recap on the first phase, we have started with the Stirling engine itself. So, as you know, Stirling engine can be powered by wide range of heat sources as thermal and biofuels, which makes it a potential competitor in this global scenario, which we need clean energy more for, and as this generation is also more aware of sustainability. So the important part of Stirling engine is the regenerator, as you can see in this image, and which exchanges thermal energy with the working fluid. So the effective design of regenerator should give high thermal storage, high transfer capacity, and a limited pressure drop across this regenerator itself. So if these characteristics are met, the regenerator can be termed as effective, and it will work in its maximum efficiency. So this is the enlarged wave of Stirling engine. As you can see, there are two pistons and a regenerator between it. So this is the focus of this work, and so what we concluded from that paper is the maximum pressure drop of oscillatory flow increases with increasing piston frequency. So when we increase the piston frequency from 5 Hz to say 60 Hz, the pressure drop increased between those complex geometries, and it also increased with the kinetic Reynolds number. So as we also concluded that the pressure drop doesn't only depend on the frequency itself, but also the inertia of the gas itself and the local losses like the profile of the obstruction and the friction from the walls. So for validation of numerical results in the phase 2, we simulated the simple rectangular section with the two inlets, and the the geometry is made from the paper itself. And for numerical analysis, I have calculated the maximum velocity and the area from the paper. So the frequency I chose is 5 Hz, and the maximum velocity from the calculation is found to be 2.361 meter per second. And the configuration I chose is 180-degree phase difference, which means both the pistons are moving in the same direction. So for the phase 2, meshes are done for the simple rectangular channel with two inlets, and element size is given as 3 mm. So for oscillating flow, inlet velocity cannot be given as a constant, and we can give it as a expression in this format. So this is the maximum velocity, and this is the frequency of the oscillating piston. So which creates the oscillating inlet velocity. So uh, from that results, the pressure across the pressure with respect to crank angle is calculated and plotted. So as you can see, there is a similar correlation between the existing paper's graph and the numerical results. Why we have a beautiful sinusoidal wave and the paper has two peaks is that they since it is an experimental paper, it had manufacturing defects, and even though it is they might have used a good motor, physically it is not possible to sync two motors to rotate in perfectly in sync. So we get two peaks in this graph. Since numerically we don't have that limitation, we get a perfect sinusoidal wave. So for this phase, I was more interested in changing the angle of the long diverging section. So and uh, investigating the pressure drop across this geometry. So this can be helpful in many ways, such as designing the complex heat exchangers as well as in biofluids. So I changed the angles from 60 degrees to 170 degrees with five different cases. I have shown the 60-degree and 170-degree case here. So yeah, for numerical analysis, Ansys is used, and it is a transient analysis since the inlet velocity itself is a function of time, and k omega turbulence model is used to capture near wall effects, and time step size of 0.01 and 300 time steps is used to, which gives us 0.3 seconds of physical time. So with these data, we can actually take a point before the obstruction and after the obstruction, and calculate the pressure drop across it. So the mesh is created again with the Ansys Fluent, but I have also done the grid independent study. So I have started the mesh size from 1 mm and reduced it to 0.4 mm. As you can see, the pressure and calculate the pressure drop across the 2 points. And as you can see, there is a deviation between the results from 1 to 0.8 mm, which has 3,800 elements and 6,000 elements respectively. But when I changed from 0.8 to 0.6 and 0.4, there is very little difference. And so 0.6 mm, there is no difference between 0.6 mm and 0.4 mm in the results. So for the further analysis of the 5 cases, I have fixed the element size as 0.6 mm and calculated the pressure drop. So regarding the results, so these are the results, and for as you can see, the pressure drop increases with the acute ramp angle and decreases with the increase in obtuse ramp angle. So in hindsight, it looks obvious, but we have to collect the data to connect it. So for as you can see in this geometry, so this is opposite of the flow. So the pressure drop is more in this acute angles, and when you see the obtuse angles, this joins with the other geometry pretty smoothly. So the pressure drop is very less. So these are the results I got. I also compared this with the original paper, and it looks comparable. Yeah. So for future work, this effect of diverging ramps can also be studied. Also, since due to the limited time, I could only simulate it for one frequency, but from the original paper, it is mentioned that increasing the frequency will also affect the pressure drop. So increasing with these different diverging sections, we can also simulate it for other frequencies and take the pressure data, which will connect to the energy efficiency savings of the product. So since pressure drop is directly linked with the energy consumption, understanding this pressure drop phenomena can help us design better products. Yeah, thank you.